Every single second, over 99,000 search queries hit Google, and thousands of orders pour into Amazon. Yet, despite billions of requests flooding the internet every minute, major platforms almost never crash. They don't rely on a single supercomputer. They use thousands of smaller servers working in unison. The unsung hero behind this seamless magic is the load balancer, a digital traffic cop directing millions of users to the right server at the exact right millisecond. Today, we are unpacking the underlying algorithms that keep the entire internet from crashing under heavy traffic. To understand how this massive traffic puzzle is solved, let's jump straight into our first chapter. Keep your eyes on the screen, because this fundamental concept changes everything. Chapter 1. Round Robin and Simple Distribution. Imagine a casino dealer passing out cards around a table, one by one, in a strict circle. That is essentially how round robin load balancing works. When request number 1 comes in, it goes to server 1, request number 2 goes to server 2, request number 3 goes to server 3, and then, the cycle repeats. Round robin is lightweight, insanely fast, and places virtually zero processing strain on the load balancer itself. However, it assumes all servers are identical and all tasks take the exact same time to complete. If server 1 gets stuck processing a heavy 10-second video upload while server 2 finishes a tiny text query in 2 milliseconds, round robin will blindly keep sending equal traffic to server 1, causing a massive bottleneck. So, how do system architects prevent a server from choking on complex tasks? Don't look away just yet. Let's unlock the next strategy. Chapter 2. Least connections for heavy workloads. To solve the limitations of round robin, engineers created the least connections algorithm. Instead of blindly taking turns, the load balancer actively monitors every backend server and counts its active, open sessions in real time. When a new user connects, the system asks, which server currently has the shortest line, and routes the traffic directly to the least busy server. This makes least connections the absolute gold standard for real-time applications, like live video streaming, multiplayer gaming, or WebSocket chat apps, where user sessions stay open for long periods and workloads vary wildly. This handles varying workloads brilliantly, but what happens when a user needs to stay attached to the exact same server? Stay focused as we explore Chapter 3. Chapter 3. IP hash and session stickiness. Imagine you are shopping online, adding items to your cart. If every click routes you to a different server that doesn't know who you are, your shopping cart suddenly vanishes. This is where IP hash comes to the rescue. The load balancer takes your unique IP address, runs it through a mathematical hashing algorithm, and converts it into a fixed numerical key. That key locks your connection to one specific server every single time you visit. This guarantees session stickiness, allowing legacy apps to preserve your login state and shopping cart without constantly querying a central database. We've covered order, workload, and persistence. But how do tech giants optimize for raw speed? Pay close attention to this final technical breakdown. Chapter 4. Least response time and ultra-low latency. In high-frequency trading or real-time bidding platforms, every single microsecond translates directly into millions of dollars. For these extreme environments, system designers use the least response time algorithm. This strategy combines active connection counts with real-time ping speeds, or time to first byte. The load balancer constantly measures how quickly each server responds to health checks. If server 3 slows down because of a background memory cleanup, the load balancer detects the tiny latency spike instantly and dynamically routes incoming traffic away from server 3 to faster nodes. It ensures end users always receive the absolute fastest performance possible. Summary. First off, I want to extend a massive thank you to all of you for your incredible focus and patience throughout this system design deep dive. Navigating backend infrastructure and load balancing algorithms takes real mental effort, but you stuck with it all the way to the end. I truly hope this video gave you a clear, fundamental understanding of how global apps scale effortlessly. To quickly recap the 4 routing strategies we covered today. First, round robin, taking equal turns across identical servers. Second, least connections, dynamically routing traffic to the server with the shortest queue. Third, IP hash, locking a user's IP address to a specific server for persistent sessions. And fourth, least response time, routing traffic to the fastest responding node for ultra-low latency. If you enjoyed this engineering breakdown, you are a true tech enthusiast. Drop a comment below letting me know which system architecture we should break down next. Don't forget to hit like and subscribe, and I'll see you in the next one.